let's discuss this linearization example. Up here, the equation I've got has a cosine in it. And the first thing you look for when you're linearizing something, the first thing you need to do is to find a solution point. So if you have a y1, that's one means it's a solution to this equation, an equilibrium solution. If you plug in pi over 4, then this equation will work. So we're going to linearize about that solution. Well, if y1 is 45 degrees, then I've got some cool relationships that flow right out. The cosine and the sine are equal to 1 over radical 2, or square root of 2 over 2. So I draw that little picture just to get going. And then here's the second key step after you pick the equilibrium point is to have an equilibrium condition plus a perturbation about it. So sometimes this is called small perturbation theory. It's called that. So this is the perturbation. And Nelson keeps the delta for a while, which is kind of good the first time you're seeing it, because he does separate in his book the perturbation from the actual variable. But in practice, you have to get used to the fact that people don't do that, right? They assume over here that when I'm talking about CMQ, it's either one of these guys. They'll assume that you know that from your experience in school. So you just perturb your variable and you stick it back in your equation. Now that's going to be cumbersome unless you use a derivative sign the way I've done it here. So I've actually put it so it's fairly clear how I'm differentiating this nonlinear, this nonlinear equation. And then you can see that when I take the second derivative then of the y1, that's an equilibrium, it's going to be 0. Right? And the derivative of y1 is going to be 0 because y1's a constant. So the only term I'm going to have trouble with is this cosine, because the cosine for a small perturbation has to be mapped out with a trig identity. Hopefully you've memorized those trig identities, at least the simple ones, cosine and sine, you should memorize. So the cosine one is really cosine, cosine minus sine, sine. So if I take the cosine function, nonlinearity, and then expand it as a trig function, I get cosine y1, cosine delta y, minus sine y1, sine delta y. Right? Everybody with me on that? Okay. So here's the third thing then you have to remember. Since this is a small perturbation, what can I replace the cosine of a small angle with? Cosine of a small angle I can replace with 1, right? Because you're at the peak of the arc of the cosine curve. And what can I replace the sine of a small angle with? The sine of a small angle can be replaced with not 0, the angle itself, in radians. So that gets rid of my nonlinearity, you see, because the cosine of y1 and the sine of y1, they're constants. They're constants that come from my equilibrium solution. So if I substitute the square root of 2 over 2 for the cosine of y1 and for the sine of y1 from this equation, then cosine delta y becomes 1, and the sine of delta y becomes delta y, and I eliminate my nonlinearity of cosine delta y. So that's how you eliminate the nonlinearity. If you were to expand this thing and you got the product of delta y, say you had delta y squared, then you would throw it away. Why? Because delta y is small. Delta y is a small perturbation. Delta y squared is neglectable in engineering. So whenever you get a delta y squared, we throw it away. So if you remember those things, then you can eliminate most nonlinearities in equations by following this procedure. So once you've substituted the nonlinearity in, you'll get a nice linear differential equation which describes the perturbation about the equilibrium solution. And we see we have a nice, so now we might want to drop the del's again if you want to drop them. And now we can go through our procedure that we should have learned in 320, right? LPT, PFE, ILT, BOT. So we take the Laplace transform, s squared plus 2s plus 2, and that gives us second order system, s squared plus 2 zeta omega n s plus omega n squared. And from here, I would expect you to be able to solve it by sight. You should be able to solve that equation by sight, okay, which we'll do, assuming after you caught up with me a little bit. So I'll give you a little bit of time to catch up.